Greetings, Caymans. Mr. Eicher here, coming at you with a lesson about linear programming, Chapter 3, Section 3, Part A. In this lesson, we'll learn the mechanics and the vocabulary of linear programming. In the next lesson, we'll do word problems and applications of linear programming. So let's jump right in. So first off, for linear programming, we have what are called constraints. Constraints is a system of inequalities, and we're going to graph that. So I'll graph the first line in blue, the next one in red, and the one after that in black. So the line in blue, find x equals 1, right here. And there's a bunch of coordinates where x equals 1, all these coordinates, and everything in between them, x would equal 1. So that would give us this line, x equals 1. And it says greater than or equal to 1, so we have a solid line since it's equal to. And greater than that, we'd shade on this side. I'm just going to do that very faintly at this point because we're going to have a lot of shading here. The next line's in red. Find y equals 0. It's right here. And there are a lot of points where y equals 0. 2, 0, 3, 0, 4, 0. A lot of points have a y coordinate of 0. So actually there's all these points that have a y coordinate of 0. And it's equal to 0, so we want to have a solid line, not dashed. And it's greater than 0, so greater than 0 would be above the line. So we have this. So far, our shading is overlapping out here in the upper right region. But we have one more line to graph. The last line we have is in black. And this line we could graph with intercepts, but how about we just rewrite it in slope-intercept form, subtract 2x from both sides. So we get that, y is less than or equal to negative 2x plus 6. So we're going to start at 6 on the y-axis. We're going to go down 2 to the right 1. And we're going to connect the dots. We have an equal to, y is less than or equal to, so we want a solid line. And then we just have to figure out shading. So if we test a point like 0, 0, here's 0, 0, the origin. If we put 0, 0 in there, we'd have 2 times 0 plus 0. Is that less than or equal to 6? Well, that's 0 is less than or equal to 6, so that's true. We're going to shade where 0, 0 is. So we're shading on this side of the black line. And at this point, it looks like our overlapping shading would be to the right of this line, above this line, and below this line. So we have this region right in here. There's a name of that. That's called the feasible region. The feasible region is important to us in linear programming. Again, tomorrow will be applications, or the next video will be applications. So this says name the coordinates of the vertices. So the vertices of this feasible region would be this corner, which is at 1, 4, this corner, which is at 3, 0, and this corner, which is at 1, 0. So our coordinates would be 1, 4, 3, 0, and 1, 0. And those coordinates are going to be useful for us, but again, today's lesson is about the mechanics of all this. So part C, find the maximum and minimum values, find the biggest and the smallest values for the objective function. So the objective function is this f of x comma y is the objective function. So we're going to take our vertices 1, 4, 3, 0, 1, 0. We're going to plug those in to the function. The function is x comma y. That's an ordered pair. We plug the vertex into that and then evaluate. So for instance, the first one we'd have 3 times the x plus the y. The next one we'd have 3 times the x plus the y. And then the last one we'd have 3 times the x plus the y. And evaluating those, the top one we get 7, then we get a 9, and then we get a 3. So which one's the maximum? Well, the maximum is the biggest one, and the minimum is the smallest one. So we would state that the vertex 3, 0 gives a maximum at 9, and the vertex 1, 0 gives a minimum value at 3. minimum value of 3. So that's basically the mechanics. What we're going to do in the rest of this lesson, I'll kind of define some of the terms for you, and then we'll do another practice problem or two. So linear programming is a process that identifies the maximum or minimum value of some quantity. And that's what we did on that part C right there, the maximum or the minimum of some quantity. This quantity is modeled by the objective function. The objective function was highlighted in blue above. This quantity is modeled by the objective function. Limits on the variables in the objective function are the constraints. The constraints were the system of inequalities that we started with in part A. And the region determined by the inequalities is called the feasible region. It's called feasible because it gives us all the feasible coordinates that we should use, all the possible coordinates we should use. If there's a max or min value of the linear objective function, it always occurs at one or more of the vertices of the feasible region. And that's what we did in B, find the coordinates of the vertices, and then plug those into our objective function. Moving on to page 2, let's look at number 2 at the top of page 2 of your notes. So we have our system of constraints. The system of constraints is going to form the feasible region. But let's graph these. The top one I'll do in blue, the next one I'll do in red, and then the bottom one I'll do in black. So we'll graph the y-intercept of 7 over 2, which is 3.5, right about there. And then we have a slope of 1/2. So we can either go up 1 to the right 2, or we could go up 1/2 to the right 1. So if we go up 1/2 to the right 1, up 1/2 to the right 1, up 1/2 to the right 1, we get that kind of thing. Or we could go up 1 over 2, up 1 over 2, or down 1 over 2, down 1 over 2. So there's our first line. It has an equal to in the inequality, so it's a solid line. And then next, the red line. The red line we could graph, you could write it as y is less than or equal to negative x plus 8. You could also use intercepts. But 8 is the y-intercept, so we have a slope of negative 1. So we'd have this line. The shading for that line, if you plug 0, 0 in, that would be a true statement. 0 is less than 8, so we'd shade below that red line. And for the blue line, if we plug 0, 0 into that, that looks like it's false. 0 is not greater than 7/2. So we do not shade where 0 is. 0, 0 is, so we shade above the blue line, away from 0, 0. Then the last line, we have a y-intercept of 8. We have a slope of 5. That's right about there. So that line would be a pretty steep line, like that. And then plug 0, 0 in to see if we should shade. So 0 is less than 8, that's true. So you shade where 0, 0 is. So you're going to shade to the right side of the black line. And it looks like our feasible region would be from here to the right of this line, above the blue line, and to the left of the red line. So it would be everything in there. So that's our feasible region. The vertices, I guess I'll highlight the vertices. The vertices for this yellow feasible region would be this point, and that point. So the vertices are -1, 3, and then the other two, actually I have this circled. So this will be a try this to make sure you can identify the vertices of the feasible region. And then on C, I'd like you to use this objective function, f of x comma y equals 5x plus 4y. I'd like you to use that objective function to evaluate where is the maximum and the minimum values. So you have a try this on B and a try this on C. And then lastly, number 3, I've graphed the system for you. Hopefully you can tell where that overlap is in that system. And I'd like you to do A and B. So state the vertices, and then use that objective function, again this objective function, to find the maximum and the minimum value of that function. Thanks for watching this video. I'll see you next time.